And I'm starting recording now. All right. So Alan, are you online? Can you hear me okay? Alan? Z? Oh, you're here.
Yeah.
Oh, okay. Somebody is online. I thought you wanted to be... Nope. Okay, could be someone else. That's okay. I got the recording up and running. All right. So we got string copy instead of string and copy, because string copy is a little bit easier, and that's a good introduction. So it copies everything, including the null terminating byte, to the buffer pointed to by destination. The strings may not overlap, and the destination string destination must be large enough to receive the copy. Beware of buffer overruns. This is actually one of the classic example of how buffer overflow exploit can work. Okay, but that's an entirely different topic. What I do want to find out is, what does it return? Okay, so what it returns is a pointer to the destination itself. Okay, so this way we can chain things. So the return value of string copy can then be used in string length, and so on and so forth. Okay, so that's why it returns the destination. And this is one way to implement string and copy, which keeps track of the number of bytes that is being copied. So what I'll do is I'm going to implement string copy itself, and I will leave it up to you guys to kind of vote on, do you want me to write it in recursive way, or do you want me to write it in a loop way? I could do it either way. Loop. Loop. Okay, so we have a loop. We have a consensus of a loop. Okay, very good. All right, so let's go ahead and do it in a loop. So we have char pointer string copy. I think the first is the destination, which is char star destination, and then the second one is the source, which is a const char source, like so. And then we're gonna write it in a loop. So okay, so we'll do it in a loop, and I'm just trying to think of what is the best way to do this. You can do this in a loop using array indexing. You can also use it just using pointers. So I'm going to use the pointer approach because that will make it resemble your homework assignment the most. So we'll go ahead and have a local variable, char, and let's see. I need to preserve destination, so we'll say old destination. So old destination is initialized to just destination because I need to return that. And knowing myself, okay, it is important to do the return right away, because if I don't do this, I'll forget. So once again, I'm writing the code in a structured way. Yes, go ahead.
Sorry, just a quick clarifying question. I forget what char pointer string copy. Like that means it's returning a char pointer. Sorry, it's been a minute since I took
it. Returns a pointer to a char. So string copy return value is a pointer to a char.
Gotcha. Okay, cool.
Yep. So with C++, you kind of read it backwards.
Right.
Yeah, so that makes it kind of not very suitable for beginning programming people.
Right.
But yet we use C++ as the instructional programming language. Yeah, that's not something I would
Java
support.
More, don't you?
Huh?
You like Java more, don't you?
Java is a good one, and then Java is probably a better instructional programming language. But back to this program. So we'll say as long as the source is pointing to something. Let me see. How should I do this? Okay. Do you want me to do it in a way that is easy to understand, or do you want to do this like with a one-liner?
Do one line.
The one-liner. Okay, I'll do the one-liner first, and then we'll kind of think of a different way to do it. Okay, so the one-liner approach is whatever destination points to, auto increment gets whatever the source is pointing to, also post increment. That's it. That's the body of the loop. So the question is, do we know what it's doing, right? So the first question is, are we dereferencing before it auto increments or the other way around? In other words, which way are we nesting? So I'll give you the two options here. Are we nesting this, which means we are auto incrementing whatever destination is pointing to, but the destination itself remains unchanged? Or are we nesting it this way, which means we are auto incrementing, post incrementing the pointer itself, but what we are actually storing to is where the pointer is pointing to? So the first or the second? It's actually the second. Otherwise, it wouldn't make sense because we don't want to change things, unless we want to change the pointer, not what it points to. Okay. All right. So to clarify, it is this. Okay. So the post increment is a little bit. I mean, it needs a little bit of explanation. Is what does it do? What is a post increment? So the post increment simply means it is after we perform the dereferencing and the assignment. After everything is done, then both source and destination would increment by one each one. So this code here is also difficult to understand because the single equal is intended. It is actually assignment. Because in C and C++, an assignment expression has a value. And that value, in return, becomes the condition of the while loop. I bet you, in your CISP360 class, they did not tell you about these things, do they? All right? But it is important, okay? This is nothing new. This is not advanced C or C++ coding. This only requires that you understand assignment is an expression. The value of an assignment expression is the right-hand side. So whatever the right-hand side of the assignment is the return value, the value of the entire expression itself. So if you want to convince the compiler that you know what you're doing so that it doesn't complain about it, you can always put an extra pair of parentheses like this and then compare this to 0. That is the more complete way of uh, finishing this whole thing, because we are going to copy everything, including the null terminator. But when we do copy the null terminator, we also want to exit the loop. So this will make sure that we do exit the loop when right after we copy the null terminator. But this kind of coding is difficult to translate into assembly code because post incrementing is not an easy thing to explain when we're translating into assembly code. So the other way to do this is not to use the auto increment, okay? But I'm saying that the auto increment method would actually work, okay? Surprisingly, it would work. So we'll basically do this part here, and then in the body of the loop, okay, let me see. I need one more paren here. So now we actually do need a body of the loop, and the body of the loop is simply to increment its destination as well as source. So this is a slightly better way to do this because we don't have to mix in the incrementing of the two pointers into the condition of the loop itself. So is that okay so far? We're still embedding an assignment inside a loop, but that's actually valid in C++. If you don't put the not equal to 0 on the outside, a lot of times you can turn on the warning, all the warnings of a compiler, and it would warn you and say, do you actually mean equal or equal in this case? Because using assignment within a condition of a loop or a conditional statement can usually be indicative of just a mistake. Because most people intend to use double equal, which is comparing, but that's not what I intend to do. This is actually what I intend to do here. Is that okay so far? All right. All right. So this is string copy. I'm not using any super tricky way to do it. So let's go ahead and look at what the assembly code is going to look like. So the assembly code is going to look like this. And once again, I want to know what is on the stack, okay? Because the focus right now is I want to know what is on the stack. What is given to me, in other words, what is the caller pushing on the stack, and what is local to me, okay, that I need to do the allocation, okay? So there are three things, okay? Three types of things on the stack. One type is all the arguments. In this case, there are two, okay? And arguments are always pushed by the caller. And then there's the return address, which is also pushed by the caller, but is popped by the callee. And then there are the local variables, which must be reserved by the callee because the caller has no understanding of how many bytes are needed by the subroutine. Are we okay on those three items in what we call a call frame? And the call frame is really just a term to refer to a region of the stack that a particular subroutine needs to access. Are we good so far with those concepts? So in this case, the call frame would include destination as an argument, source as a parameter, sorry. So both of these are parameters. Old destination, which is a local variable, as well as the return address. But the way it's going to look like on the stack is at the highest address is my second parameter, which is source, and then followed by the first parameter, which is destination, and then followed by the return address, and then followed by the local variable that I call old destination, because I need to save that so that I can return that later. All right, so once again, this is at the highest address, and this one as the lowest address of this particular call frame. And when everything is done, initially the stack pointer points here, okay, at entry point. But eventually, after I have done all the allocation, after the allocation of the local variables. So the allocation of space for the local variables is the responsibility of the subroutine being called because the caller does not know how many bytes we need to reserve. All right, so there are a few things we need to do. I always start with returning first. So I do a LDBD, pop the return address, and then just continue execution at the return address. These 3 bytes, these 3 instructions are needed by every single subroutine. So I always start with that. And then I need to allocate and deallocate the local variables. So how you want to do this is entirely up to you. This particular subroutine can be implemented in a very quote-unquote organic way. Okay? Is it a good way or is it not a good way? Kind of depends on your perspective. Okay? So once again, now you have a vote opportunity to vote again. Do you want the organic way, which is very kind of more optimal, but it's very specific to this particular implementation, or do you want the more run-of-the-mill, will waste code, will waste efficiency, but it's easier to read?
The first one.
Okay, so the first one, any second?
Second,
easier to read. So we'll go for the easier to read one, and then we go back to the more efficient one. Would that be okay? So we're just prioritizing which one to present first. Okay. So we'll go for the easy to read one first. So the easy to read one is going to require a bunch of labels. Okay, so we'll say StringCopy old destination being 0 because after everything is allocated, this is at the offset of 0 from where the stack pointer points to. That's what the 0 is representing, is the number of bytes between where the stack pointer points to and the thing that the label is corresponding to. And then we have the next one is string copy local variable size. This is a label so that I can use it to remember how many bytes to allocate and how many bytes that I need to deallocate. And that's always looking at the last local variable and the size of that, just add to the size of the last local variable. Since we only have one single local variable, it is both the first and the last, okay? So the size is simply 1 in this case. We just need 1 byte for all the, quote-unquote, all the local variables in this case, because we only got 1 local variable, and it only needs 1 byte. And then we have the return address. Typically, you don't need to name the return address because it is unlikely that you need to access the return address. So we can start with destination. So string copy destination is going to be StringCopy LVS, local variable size 1 plus. Let me think. Yes, it needs a 1 plus because that 1 is corresponding to the return address. And then we have the second parameter, which is source. So StringCopy Source is StringCopy destination 1 plus. And this 1 plus here is referring to the size of the source. Okay. So are there any questions about the correspondence between the label definitions and the critical picture in comments about what is supposed to be in this call frame?
I was asking about after the colon, that's the value.
Yes, you can give a label specific value using this particular format. If you leave it blank, then it would just use whatever address is corresponding to that line of code. But you can always give it specific value by using a RPN, reversed Polish notation, or postfix expression.
And that value is the size of the, what is that value?
It would be the offset to each item, except for LVS, which is the size of the local variables, or the total number of bytes needed by the local variables. Are we still doing okay so far with this? So all of this stuff here has to do with the caller callee agreement, plus something that only the callee understands how to do, which is the local variable. All right, so after this, I write the code in structured way. So I would allocate, and then I'll deallocate, and I'll do all the things that I need to do in between. So to allocate, we just do a ldaa. Well, it's best not to use RegisterA because it has a special meaning, because we need to return a value at the end of this particular function, and RegisterA is used to return a scalar value. So we'll use register B, okay, StringCopy LVS, the number of bytes we need to reserve for local variables, and then we have to subtract that much from the stack pointer to allocate for the local variables. And then when we are ready to return, we do the reverse, because we no longer need the local variables, so we are deallocating the space that was previously used by the local variables. So once again, I am not commenting the program intentionally, so that you guys have a chance to do it. But I'm verbally describing, which means if you see this program, you can comment it, and then you can listen to the lecture again to see whether you wrote the comment correctly. Also, after we run this code, you can actually start to see what is being used on the stack for what purpose. Okay, it will be pretty obvious in this case. Cool. So now we can actually go ahead with the first assignment statement. So we have ldaa string copy destination. So this is just the offset. So we are putting the offset from where we can find destination as a parameter into register A, and when I said offset, it is an offset from where the stack pointer is pointing to, which is the local variable O destination. So this is the offset, add AD, is adding the stack pointer value to the offset of where we can find the destination relative to where the stack pointer is pointing to. So at the end of this operation, what can we expect in register A? I know I just said a lot of words, okay? So let me say that one more time. The first instruction, the LDI. Oh, okay. Yes, so the LDI instruction is loading register A with the number of bytes from where the stack pointer points to where we can find the destination. So it's just an offset. The second instruction, add AD, is going to add the value of the stack pointer to register A, which before this add instruction is containing the offset of where we can find the destination from where the stack pointer is pointing to. So after the add AD instruction, what do we expect in register A? Yep, the address of the destination. Okay, the address of the destination. All right, and well, that's all good, but I don't need the address of the destination. I need the value of destination. So I need load ldaa to dereference the address of the destination. So now we actually get the destination itself in register A. And then I do something almost exactly the same with register B, except this time I'm using old destination. And instead of a load, we have a store, because that's what the C code is supposed to do. We're supposed to change the value of local variable old destination. So we have a store instead of a load. And indeed, we are storing whatever is in register A, which is representing the value of the right-hand side of this line, to whatever register B is pointing to, because register B is the address of old destination at this point of the program. Yes?
I'm sorry, I might have missed it, but are we just assuming that register D is the stack pointer, or do we define it?
That's our convention now, right? So register D is always the stack pointer.
Okay.
So unless I specifically say in this context, the register D is something else, register D is always the stack pointer.
So we no longer need like the ldaa D0.
Well, this is inside the subroutine, so we assume the stack pointer is still healthy by the time we get here.
Okay.
Yep. All right, so that finishes the first, this statement here. So now we can get to the loop. So the loop is, a little bit longer, okay, because we need the name of the subroutine followed by the loop, and then followed by 1, because in case I have multiple loops here. And then we also have a begin. So, but every time you have a begin, you can expect an end. So there we go. So now I have defined the beginning and also the end of the loop. So in between, we need to perform the checking here. So we got a few things to do. The first thing we need to do is to retrieve whatever the source is pointing to and dereference it. And then we have to copy that to whatever the destination is pointing to. And then we compare what I just copied and see if it was non-zero. If it is 0, we exit the loop. If it's non-zero, we get into the body of the loop. Is that okay so far? Are there any questions about the C code itself? Because if there are any questions about the C code itself, we can't talk about the implementation in assembly. So we're still good? All right. So let's go ahead and do this part. Okay, so later on, I'm going to give you guys like a super simple C code, C program, to help illustrate what I said earlier, which is an assignment expression has a value, and that value is the right-hand side of the assignment. So I will get to that point in just a little bit. All right, cool. So now what we do is we have to get to source first, and this may be the more challenging part, is how do we figure out the order of doing things? So you kind of have to think in your head of what this is all doing, and then you have to think about what do we need to do first. So I typically work with the right-hand side of an assignment first, figure out what that is supposed to be, and then work out the left-hand side, finish the actual copying of the value, and then do the rest later on. All right, so let's go ahead and do that. We need to get to source first. So now you will start to see the pattern of, okay, getting to the source. This is the offset. This is the address. This is the parameter itself. And this is what the parameter is pointing to. Okay? So this program is really useful from the perspective of your homework assignment, because it has some of the elements of your homework assignment, even though the control structure part is actually quite a bit more complex than your homework assignment. But from the perspective of what we are doing and assigning and accessing what the pointer is pointing to, that part is common to what your program has to do. All right. So now that we have the right-hand side, we can work on the left-hand side. So the left-hand side, this is going to look a little bit familiar. Okay, we've got the offset into B. We now get the actual, oops, I just did something to the other side. Not sure what I did. Okay, so I didn't change anything Oh, okay, that's just a line of comment, so I think I'm fine. Now we have the address, and then we get to the parameter, and then we store to whatever the parameter is pointing to. So we are not changing the parameter itself, we're updating whatever the parameter is pointing to. Yep.
What LDAA twice?
Well, we did it twice because one to get the value of the parameter, the second one to dereference the parameter. So this is where you really need to track what is in a register with every single line of code. Okay, I can talk about it, I verbally describe it, right?
Mhm.
But we'll run it later too, okay? And then when we run it, you can actually get to see what a register is containing at any particular moment, and then you then put the comment and your own understanding in your own words into the comment of this program. Just remind me to upload it so you guys can get the source code without the comment. Then you can just add your own comment and your own understanding of the concept into the program itself. Is that okay? All right. I mean, I could have just commented everything, put it into a module, publish it, and be done with it. And trust me, most people will read that whole thing and not gain an actual understanding because reading, especially when you understand what every single word is not the same thing as actually understanding the concept. It is only when you are doing the figuring out part that you will start to understand the concept. All right, so that is doing just this part here. And the value being copied is in register A, so I need to check whether it is 0 or not at this point. So to check whether something is 0 or not, the trick is to use AND AA to kind of push the register through the ALU and therefore affecting the Z flag. And if the Z flag is indeed set, in this case, it means register A is a 0, which means, woohoo, we are ready to get out of here. So to get out of here, we just have to go to string copy while one underscore end. I predefined that label here already. And usually I can also do a JMPI here back to the beginning, which is string copy while one begin. Oops. And now I need to put the code in between. So what I'm putting here in between will be the actual body of the loop. Because at this point, at the not so blinky cursor, but nonetheless cursor, at the cursor, we have branched away if it is time to get out already. But since I have not done that, that means it's not time to exit the loop yet. And yet we have not gotten to the bottom of the loop, which helps, which basically goes all the way back to the beginning to perform the condition of the loop again. So this is the actual body of the loop. So within the body of the loop, what do we need to do? Well, we need to add one to destination as a parameter. We also need to do the same thing with source. So assuming that we are not optimizing the code, we're going to have to redo everything from the beginning. So we say ldia with string copy destination, add ad ld ba. This time I do want to preserve the value of a because a contains the address of destination, b contains the value of destination, increment b because that's what we're supposed to do, which is incrementing, and then store that back to wherever destination is. Okay, so we just do the same thing here, and then I'm just being lazy here, copying these 5 lines because the second thing we need to do is, well, let's do exactly the same thing with source, auto increment source, just like that, and that's the body of the loop. So after the body of the loop, before we lose track of the local variable o destination, we better make sure that we make use of it and specify the return value. So that's what we're going to do. Okay, ldia with string copy old destination, ldaa. Oops, forgot about this. Add ad first. So before you do, if you don't do the add 80, you just have the offset in RegisterA, which is not an address. So you have to add the offset to the stack pointer to get to the address of something that is living in the call frame. And then we can now ldaa again to get to old destination. And that's our return value. So we are pretty much done at that point. All right. So this, I think, this is going to implement the C code. And now we can wrap around this whole thing with a main program. And we'll start with a no-out instruction, jmpi to main. And then in main, we'll just set up something to test it. Okay. So here's main, and we know main has to halt at the end because it is not really a subroutine. There's nowhere to return to. So how do I want to set up the test here? So we'll go ahead and say this is the C code in main, and we're going to have a local buffer. So the local buffer is a char array, and I'm just getting too lazy. I'll just give it 10 bytes like so. And then we'll say string copy to buffer from the literal string of, once again, tag, like that, and then return 0. Okay, so that's the C code. In assembly code, we know from the previous class that in order to use a literal string, we need to define a quote-unquote hidden label. So we'll just go ahead and give it some weird name like this as the start label of the literal string. Did I talk about the literal string last time? I think I did. The thing is, in this class that I talked about string length in a recursive way. That's when I talked about how to make a literal string, right? Okay, so now we have to define the bytes. The first byte is corresponding to the ASCII code of T, and you can do the counting on the hand, right? So you have A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T. So that's 20 by my count. With A being 1, T is 20. So the ASCII code of lowercase a is 65, so it's 64 plus 20 in this case. That's lowercase t, and then lowercase a is 96 1 plus, and then k is A, B, C, D, E, F, G, H, I, J, K. So that's 11, 96, 11 plus, and then plus a null terminator. So that's the literal string. So when we need to execute main, main also has a local variable. So we need to take care of that too. So we have main buffer being defined to be 0, because after I allocate for the local variables, the stack pointer should point to the beginning of buffer, which is an array of characters. So if I want to do the same thing, to be consistent, the total number of bytes I need to reserve in this case is going to be main buffer plus the size of the buffer, which is 10 bytes. And those are my local variables. So now I'm going to allocate and deallocate for the size of the local variables. So now we got, before that, we can also initialize the stack pointer to 0. And then we can now do a LDI A with main LVS. We do a subtraction to allocate. And then when we are about to end the program, we do an add to deallocate the local variables. And then in between, I can refer to the label to access the local variable called buffer. Are we good so far? Any questions with any line on either side of the programs?
The main LVE, I think you have type of LVE and LVS.
Oh, yeah. Yep. The assembler can catch that, so I'm not, but thank you. I'm not too concerned about typos. Anything the assembler can catch, I'm not too concerned about it. Any other questions? We all good?
So where does
Question.
the I2HR come in?
Sorry?
The I2HR, that array, is that not going to be reflected in main at all?
Oh, we will use it,
Okay.
when we set up the arguments.
Okay.
Yep. Any other questions? Okay, if there are no questions, we're going to continue. So now we need to handle the function call, and we need to push all the arguments, last argument first. Okay, so we're going to push that first. So ldia with that kind of bogus label name, decrement d, stda. So we just pushed the literal string on the stack. When we use double quote, I think I said this already in the previous class, double quote means we're dealing with a string. So it really is the address of the first byte of the literal string. It is not the characters TAK. Okay? So a literal string is a pointer to the beginning of the entire string. So we got the second argument pushed. It's time to push the first one. So we have ldia again, and this time we have strcpy. Oh, nope. Okay, this is main buffer. And this is a little bit awkward, okay? Because right now, instead of having the stack pointer to point to the beginning of buffer, it is pointing to one byte below where the buffer is, because we just pushed the second argument on the stack. So that means if I want to get to the beginning of buffer, I have to remember the stack pointer is not pointing to where I usually have it pointing to, it is pointing to one byte below. So to compensate for that, I have to add one to the label buffer. And before I do add AD, and then after this, I got the address of buffer in RegisterA already, and we can push it on the stack. So we decrement D, stda. So now we got both of the arguments pushed on the stack. It is time to push the return address. So to push the return address, we have ldia dot 5 plus, and the spaces between the 5 and the plus is actually important, because otherwise the parser cannot identify, oh, this is one thing, this is another thing, and that's an operation. Okay. And then we can do stda. This is pushing the return address. So now we got three things pushed on the stack to prepare for the function call. We got the literal string pushed first. We got the address of buffer pushed second. And then we have the return address pushed last. So the return address is where the stack pointer points to right now. And then we have a JMPI to the subroutine that we are calling. When the subroutine returns, which is where the cursor is, we have to deallocate the arguments. There are two on the stack right now. So increment D. Which two arguments are we talking about? The address of buffer and also the literal string. Those are the two things on the stack that I, as a caller, needs to deallocate, because the callee is only responsible to pop the return address, but it's the caller's responsibility to deallocate for the arguments. So now we got everything deallocated. We get back to the end of the main function, and I think it is done. Okay, not 100% sure, but looks to me it is done. All right, so let's go ahead and run this code. Okay, and there we go. We just saved it, because one of my other favorite mistakes to make is not to save the file and then start to run it. So now we go to Documents, CISP310, and go to RiverSpider. If you have not set up RiverSpider, it's a good idea to do it. It might take you a little bit of time, like maybe 15 minutes to half an hour, depending on how fast you can read and also follow the instructions. But I can assure you, those half an hour, even if it's an hour, it's time well spent, because this way you can actually run the program really quickly and easily, and also be able to see exactly what is going on when the program is running. All right, so we'll go ahead and run this code, which is StringCopy TTPASM. I'm not even sure that it's going to assemble, because I might have some typos with the labels and whatnot, so we'll see. Okay, it did not want to run because I probably typed in some
One label has a LDE at the end, right?
Yeah, so well, I got an extra underscore in this one, so that's line 45. So let me go back to the editor, which is here, line 45. Yep, sure enough, there's an extra underscore. Might as well check for other things to see if there are any other mistakes. Yep, main LVS, right?
Correct.
Yep, there we go. But anything that the assembler can catch, it's not too big of a deal, because it's not going to be taking a lot of time. Because most of the time, it's a typo of some kind. Like, well, like, oh yeah, that's it's supposed to be LVS instead of LVE, and then the other one has an extra underscore. Pretty easy to spot, pretty easy to fix. All right, so we'll make sure we save the modified code again. Go back to try to run it one more time. Okay, there we go. All right, so this time the object code is good, simulation is finished, and the trace is all done. All right, so what are we supposed to do at this point? Most people will say, well, go to the analysis tab and see if your TAK is copied to the buffer. Where's the buffer? What location are you checking? Okay, so what we want to do is to figure out how the stack is supposed to be used in this case before we even head over to check whether the program ran correctly or not. Because otherwise, we won't even be able to tell whether it ran correctly or not. Okay? So let's go ahead and do that. And we can go ahead and use a spreadsheet to try to figure out what is on the stack. So let me go to my local spreadsheet program. All right, so this is just a regular spreadsheet program. You can use Excel for this purpose because all we are doing is we're just documenting things, right? So we have location 255, and this is the previous location -1, and so on. I'm using base 10 in this case just because normally it's easier for us to look at base 10 numbers. So where do you think buffer is?
Where are we in the program? Are we at the very beginning?
We are at the very. There's only one subroutine that has buffer, which is main.
Okay.
So where do you think buffer is? The buffer local variable of main is located. Which rows of the spreadsheet are we talking about?
Row 1.
Okay, row 1 would be one row that has buffer.
There's 10, right?
There are 10 bytes, exactly. So row 1 is actually corresponding to buffer 9. This is corresponding to buffer 8. And I'm just going to say blah, blah, blah. Okay, so if you look at it this way, where do you think you can find buffer 0? Which row in the spreadsheet am I supposed to find buffer 0?
2, 4, 5.
At 10, row 10. So 26.
Yep. Because you have to remember to add 1. Okay, it is the row first number minus, okay, it's 255 minus 246 plus 1. That would be the number of bytes that we have in this range. You have to remember the plus 1 because the indexes are inclusive. So we have buffer 0 over here. So that means these 10 bytes are being used to store the local variable buffer in main. So where do you think TAK is going to be, TAK?
Right below that. So the ending of TAC would be at line 11. So
No, wait. Okay. Remember what string copy is supposed to do? It's supposed to copy to the destination, where the destination is. So buffer is the destination. So that means where the cursor is,
Mhm.
that's supposed to be where T is. Okay,
Okay.
the T of TAC is supposed to be here. So T is here, A is here, K is here, and this is where we are supposed to find the null terminator. Are we doing okay so far? All right. So at least with this much, I can now go back to the analysis tab and check these locations and see whether these 3 bytes are indeed at those specific locations or not. Now, this is where you can say, it would be kind of nice if I can look at the locations in hexadecimal. Well, I would agree with you.
You
So
can add the column right behind.
yeah, we can just use we can do it before or after. Sounds like Jeopardy. Before and after. Insert column before. There we go. And I'm hoping LibreOffice also has base conversion. So dec to hex. Um, this thing here. Yep, it did. Very good. That makes our job a little bit easier, right? There we go. And we might as well just get it. Do it like this. All right. Well, since we're here, well, okay, one thing at a time. Okay, so we want to double check to see if the program worked or not. So now we head over to the trace, which is in the browser, and then we go to the analysis tab, and we want to go to the end. So summary tells us we have 208 rows, so I can skip all the way to that first. And I just did something to hide the analysis tab. It's supposed to be here. Okay. So we want to go to G202, which is supposed to be the end. Was it 202? Okay, this is where the halt instruction is. All right, so how do we know whether tag is written to the locations that they're supposed to receive, right? Okay, let's check the spreadsheet again, where we are supposed to find those bytes. All right, so T is supposed to be at location F6, A is supposed to be at location F7, K is supposed to be at location F8, and then the null terminator, which is 0, is supposed to be at location F9. So now we want to look at any update to location F6, okay? So let's go back to the trace and see how we can do that. All the memory write is documented by column C. So now we can say column C, and we want to look up, okay, so we look for find and replace. And you can always just go like, F6 equals to. The asterisk is needed because every single cell here is going to be dereferencing location equal to, because we are actually changing the location on the left-hand side of the equal. So we're looking for something like this. This is the pattern that we're looking for. And we can just say find. It is getting a 5-4. So the question is 5-4 the ASCII code of uppercase T? Looks about right to me, okay? But we can always double check, okay? And then the next location is F7, which is lowercase a. Okay, let's find that. Look, it's 6-1. I'm pretty sure that's lowercase a. And then the next one is location F8. And it has 6B. So that's supposed to be the K, okay, TAK. And then we have a null terminator, which is a 0. This one is easy to identify at location F9. And we find it one more time and go like, yep, we got a null terminator. So I'm feeling fairly confident that the program did what it's supposed to do. And if I go all the way to the end, I want to look at the stack pointer. The stack pointer is back to location 0, 0, which is good. I balanced the stack. I finished all the copying, and so the program did what it is supposed to do. Now, getting back to the question, okay, because some of you probably have this question in your head right now, or has been in your head for a while, is when we implemented StringCopy, sometimes we have double ldaa, and other times we only got one single ldaa. Sometimes we have an stb blah blah instead of ldaa. So the code is all in here. Okay, the effect of every single statement is already in the analysis tab. This is where you can go in and do some detective work. It's like, okay, I'm concerned about this line with this code here. What did it do? Well, let's find out how we got the actual content there, right? So we're going to look up column C one more time, and then we use find and replace, and let's just say we want to look up F6 again, like so. And this time the question is, how did it happen? How do we copy uppercase T to the first byte of buffer? Well, the nice thing of having a complete trace is you can actually execute the program backward, right? Because we know this is location 17 and the instruction is the ST instruction. Not surprising because ST is the only instruction that can store or update RAM. But how did we get B to point to the location of the first byte of buffer? How did we calculate that? Oh, wait, look at this. B just got updated here. What instruction is updating that? It's a LDBB instruction. Okay, but how did we get to F6? Before this, B was F4. What is in location F4? What is in location F4?
We know it's something in the buffer because we just labeled it, right?
Well, we are not quite done with labeling everything on the stack, right? So what is at location 245, 245 in desiccant? In other words, after I allocate the local variable buffer, we proceeded to call the subroutine, right? So what is the first thing that we push?
Return.
Nope, return is always the last thing to push.
The second parameter,
The second argument, yes. And what was the second argument?
not the destination, but
The source, which is the literal string tag, right? So this actually should point to the underscore something label, right? The internal label. Okay. And what about the location 244?
that would be the first argument.
There'll be buffer, right?
Right.
The address of buffer. And we know where the address of buffer is, right? You
Right.
look at this picture and it's like, this is buffer and it's supposed to be F6. Okay.
So that's where that store BB is, because B had F6, which was the buffer, which is the destination, right? The first parameter.
Okay, I'm not quite sure which instruction we're
it was like
talking
the
about.
line we were just looking at
Yeah.
in the analyze.
But you're making that connection in your mind and you can jot it down. That's important, okay? Because I cannot speak what is in your mind. So when you have a thought and go like, I'm making that connection, it's important that you write it down on a piece of paper, type it on your computer or whatever. Okay, so you got to document the way you think and the way you make connections in the class. All right, so we got the second argument, the first argument. What about this place here? What is supposed to go here?
Then the return.
The return address. Okay, because we got the second argument, the first argument, and then we got the return address. Okay, so we say return address back to main. And what about here? Are we really sure that we got this low? I'm pretty sure. But what is supposed to be here?
All destination.
Say it one more time.
All destination.
O destination. Very good. Okay, because that's my local variable O destination of string copy. Is that okay? So when we overwrote the location F6, this is the clue that we got. Okay, and how do we get here? We have to get here because of this location. Okay, because the parameter is living on the stack. It has its own address. So we have to first compute the address of the parameter. Then we get to the value of the parameter. Then we get to the value that the parameter is pointing to. So there are a few levels of indirection here, and you have to be able to look at the source code and be able to say, oh, I know exactly what is in each register at any point of time. Register A is an offset, register A is an address, register A is the value, register A is what the value is pointing to. So you've got to be able to actually be able to understand all that stuff. And it's not just a pattern thing. It's not just like, okay, so the first one is always an LDI, followed by add something, add the stack pointer to something, and then we do an LD. It's not just remembering the pattern of how the instructions appear in which order. It is actually being able to understand what is in each register at any point in this code. It's important to be able to point that out. Are we good so far?
I was still looking why is twice. Why is it doing the same thing?
It's not doing the same thing because register A has something different for each of the LD instructions. I mentioned that already,
Yeah,
right?
you did that. I don't see how that happens if you're doing the same.
That's what the trace is for. But this is why you want to do the trace, or at least bookmark and take a snapshot of the trace right now. So let's find out which line we're talking about. Okay, you're talking about this line, which is line what 27, and then we go to the trace. Okay, we go to the trace. We go to line 227. Right, column F is the line number. So we get to line 27. And then what you need to do is to figure out what are we putting into register A. This is the offset, this is the address, this is the value, and this is what the value is pointing to. So this part is important for you to make that connection. I can explain it, which I just did, right? Twice or 3 times, because as I wrote the code, I explained 1 time also. But until you actually spend the time to go into the trace, to actually ask the question, what is this instruction doing? And at the end, when this instruction is done, what is in the register? And compare that to the picture of the stack. Until that time, I can write all I want. And then I'll just be saying what I know, but it doesn't mean that you can easily absorb that information because you really need to kind of do this in your own way in order to make that connection. Yep.
So you're saying address 33, so we can see on the left hand side as well, the address 33 is pointing to the value that is 54.
Yes.
That is over there, it's very clear.
That would be a good observation.
And also, okay. There's like,
Yep.
yeah, that's, yeah.
Yep.
Okay. Yeah, because it was confusing at first, but I guess like register A has it has the address that is 33, or I mean, it points to the address that is 33.
Yeah. So if I start with this line again, so LDIA with StringCopy _ source would put the displacement or the offset into register A.
Yeah.
Offset from where to where? From where the stack pointer points to source as a parameter.
Yeah.
Okay, that's just the gap between those 2 items. Once I add the stack pointer to it, then it becomes the address. Because if you get the offset from where the stack pointer points to blah blah blah, and you add that offset to what the stack pointer really is, guess what? You end up with the address of blah blah blah. So F5 is the address of the parameter source, which is helpful, but that's not what I really want because the code wants to find whatever source is pointing to. So I have to dereference it once to get to the parameter itself. So the parameter is 33 in hexadecimal. That was what initially was pushed by the caller. Is that okay? But 33 is just an address. I need to get to the byte because I'm copying the content of the source to the content of the destination. So I need to dereference it one more time to get to the ASCII code of T, which in this case is 54. But tag, how do we know that 54 really is uppercase T and it is at location 33? The assemble tab is going to help. So we have to go to the assemble tab like this and go to location 33. Okay, so we just scroll down to location 33 and you can see this is where I'm supposed to put in TAK and the null terminator. How do we know we push this on the stack? How do we know that the caller or main actually pushed this on the stack? You look into the caller's code. The first thing that we pushed was, where was it? Here. The LDIA instruction is loading a 33 into register A. So there are multiple pieces here that you need to kind of glue and connect in your mind. So we have the source code, we have the assemble view, which tells you what are the byte values at different locations. And then there's the actual trace of what happens when this code executes. So all of those need to be connected to, guess what? To the C code. Because that is the focus of this class at this point, is making the connection between the C code and the assembly code. Are we okay or not? Now, when I ask that question, I'm asking, are we understanding the concept here or not? And I'm also asking, do you know how to study for this class at this point? Because even though we only got 3 lectures left, not, well, that's including the final exam review, it's still important for me to make sure that you guys know how to study at this point. Because it's not just reading something, because it's hard to convey that. But if you have this code in source code, in assemble view, in the analysis tab, and you can make all the connections all the way back to what the original C code is wants to do, then you have a good understanding of what is happening at this point. Yep.
I guess I personally would need like a reminder of which ones in the assemble tab and the analysis tab, like the columns, which one are those exactly? Like maybe a label would be great, or just like.
They all got labels.
Oh.
They all got labels. This is the source tab.
I know what I meant was like the columns, for example, in assemble.
Mm-hmm.
Um,
It got labels too.
oh, I see.
So if you hover over,
Oh,
yeah. So except for the first column, which is column A, it also has its own label. This is basically the same as the source, but with all the comments cleaned up. And then you have column X being the opcode, and then column Y being the immediate value, if there's one.
okay.
Yeah. So they're all kind of labeled. And then the analysis tab, if you go all the way back to the beginning, it's also labeled. So we have the address of the instruction. Is it reading any RAM location? If so, which location did it read and what is at that location? Did it change any RAM location? And if so, which location got changed to what? Did we change a register? If so, which register got changed to what value? Are we updating any flags? And this is a new feature. Column F and G are new because it also points you back to the source code on which line and what is the code on that line. If you use comments, it will show up here as well. So that's why the first thing you want to do is to add your comments to the source code. So this way, when you look at the trace, your comment would also show up in column G, and that will help you make all the connections. I mean, is that important? Is that okay? I mean, and then you also have to reconstruct the stack, as we execute the code.
And
Yep.
execute at would be
The PC, the program counter,
program counter.
which means 00 is the address of the no-op instruction, 01 is the address of the JMPI to main instruction, 37 is the first instruction of main, which is initializing the stack pointer. 39 is the first instruction to adjust the stack pointer to allocate for buffer. 3B is the second instruction that actually does the subtraction. And 3C is the first instruction of pushing the literal string on the stack, and so on. Yes, I can remember the sequence. All right.
I have a question. Why is the sign flag 1?
The sign flag?
Line 9?
Well, that's a good question. So this is after. So the way we read this is first to ask, okay, what did we do? What did we do? It's a subtract instruction.
Okay.
What are we subtracting from what? Okay, it depends on what is in register D and what is in register A. Register A has a value of 0A, which is 10. Register D has a value of 00. So this subtraction here is basically asking what happens when you subtract 0A from 00 in hexadecimal. And the rest goes all the way back to binary subtraction and binary comparison. Yes, this class has one really, really long continuity. Is that okay? All right. So I got about 10 minutes to implement the recursive version of StringCopy. Shall I do it? Okay. Since I did promise you guys that I would do that, right? Okay. So I'm going to leave this one alone, okay? And I'm just going to make a new program so I don't lose track of the one that works and it's easier to understand. Actually, I may not have enough time to fulfill all the promises because the other one, okay, I'll just go ahead and, okay, I'll make a copy first because the first one I want to do is, so the first one I want to do is to copy StringCopy TTP ASM to organic. Okay, because that was one thing that I said that I could do is not to use this kind of more structured way to do it, but to do it in a much more organic way, which is good and bad at the same time. It's more efficient, but two, if I were to read my own code like 4 hours from now, I would go like, what is that? But we can do that, okay? Because it's still a useful exercise because it would look like you're trying to solve a puzzle, which it is, okay? But it's also important because by practicing solving this puzzle, you are also practicing how to, your understanding of the material. So 10 to here, delete. All right, okay, so let's do it the kind of more organic way, okay? So the more organic way to do this is to kind of not use a structure way, and I'm just gonna say, destination is not even needed because I just need to copy the spirit of the code, but not so much the implementation of the code. So I'm gonna copy the stack pointer to register C in this case, and then I go like, I better remember what destination has at this point, but I don't even need to do that because I think I got enough registers to play with that I don't really need to do any of this. So I'm just going to put source into one register, put destination into the other register, and I still have one spare register to play with, and that's all I need to do. All right, so we'll increment C so that register C is pointing to destination, and then we'll do a LD B C, and I have to write this down because otherwise I'm not going to remember that B is supposed to be the destination. Not quite yet, okay? Because at this point, it is the destination. Increment C one more time, and then put A is my source, okay? So now I'm just going to use register A, B, and C to finish the loop here, okay? So let's see whether it is doable or not. So we have to first dereference register, the source is register A. Register C is now available again. So I'm going to say while one, okay, string copy while one begin. String copy while one end. And then the first thing we need to do is to dereference source, and source is already in register A. So I do an LDCA. So C is now whatever the source is pointing to. And I can now store that to whatever registers B is pointing to, because guess what? Register B is the destination. So now I can say and CC to see whether what I just copied is 0 or not. If it is, I'm done. Let's get out of here. If not, I got some stuff to do, okay? Whatever I need to do, the last thing I need to do is to go back to the beginning of the while loop. So now I can implement the body of the loop, which is to increment the 2 pointers. And that becomes like super duper easy because the destination is register B, the source is register A. And when we're all done, we get out to when we get out of the loop, I just have to go back onto the stack to retrieve the destination because that's supposed to be my return value. So at this point, I can CPR CD again, increment C LDAC, and I think we're done. So this is a lot shorter compared to the previous version, but at the same time, you need to keep track of which register has what. A little bit more difficult this time because it's not making use of the symbolic names. You cannot just say, oh, this is using that symbolic name that has source in it or destination or O destination in it, and I kind of know which one we are trying to access. This one is like, nope, we're just playing with registers A, B, and C. But which one has what? You kind of need to track it. Okay, so I claim that this is done. And we'll find out whether it's done or not. And I just made a mistake here because I forgot to make a copy of this. So let me make a copy from here because I want to give you the source code of this one. So this one is still the same as the one before. So I want to copy and paste this into a different file because otherwise you won't see that. CP string copy TTP. Nope. Have to lengthy string copy.ttp exam paste. All right. So now I have the old one, which is the long lengthy one. And now that we have that done, we can go back and run the shorter one, which is actually the current TTP ASM. I mean, string copy TTP ASM. All right, so let's see whether it works or not. Now, the items on the stack are still the same, okay? Minus O destination is no longer needed. So we'll see. That is not looking good because it looks like it's got stuck in an infinite loop. I think it times out. Yes, it times out. But the length of the trace is going to be long. But this is great because I can now show you how to debug a program. We got 2 minutes left. Do you think I can do it? Yeah, you can see how this is taking a lot longer this time because the trace is like super duper long. Yes, I'm wondering when Google is going to say, "Tag, stop doing this to our server. Go away." All right, so, okay, I'm just going to start to debug the program just right here. All right, so register C is pointing to the return address. Register C is pointing to the destination. Register B is the destination. And right here, that's why. Because I've incremented the stack pointer instead of register C, so the source was from the wrong place. So that's why. Okay, so I think we got that problem fixed. And then we'll go ahead. Google is thinking right now, not you again. It still looks like it's getting into a long looping thing. All right, so if it's looping like that, it means it's not getting out of the condition, the loop. So we put whatever source is pointing to into register C, and then we store that into whatever B is pointing to, and then we check whether register C, which is what we're just copying, is null or not. If it is, we get out of the loop. If not, we increment the 2 pointers. Yep.
You're not incrementing C.
I'm not incrementing C. You mean here? Well, this is returning the wrong value. You're correct. I should be incrementing C and not incrementing D, but it should not lead to an infinite loop like the way it is. All right, so it's still stuck in an infinite loop. All right. So I'm going to ask you guys, what are you going to do when your program is running into an infinite loop and it's just taking way too much time for the whole thing to finish? How would you debug a program like this? I have an answer already, but I want to see if you guys can think of a technique to do this.
It's not we could use like a toggle with debugger and then use the toggle.
You mean the clock thing? Single clocking the whole thing?
No, the red.
The red
The
thing.
breakpoints.
Oh, you cannot do there's no breakpoint. Okay, this
Oh.
is using my own tool, so there's no breakpoint whatsoever. So let's see what the analysis has to say first. Okay, it is, the summary says we have 13,712 lines, which is definitely wrong, right? So we know it's in an infinite loop, and infinite loops are pretty easy to see because you can actually see the repetition of stuff. And this is way wrong. Okay, we continue execution at F6. That is indicative of a problem. So JMPB ends up at location F6. So that means we popped the wrong thing from the stack. And that has to do with, oh, this is, okay, wait, did we fix the source code here? When we had this, incrementing D, that was the issue. And then we also, oh, okay, now I see. Because this also was wrong. Remember, we fixed that one too. This is also supposed to be increment C and not increment D. Okay, so I think when we run this one more time, it should do it correctly.
I felt like you saved it after that.
That is a good question. Did I even save it? Nope, I forgot. That's one of the favorite thing I do,
But that's
isn't
funny
it?
because the code just said it was good.
Yeah, the code is good, but it's still wrong. It's syntactically okay, but logically wrong.
Gotcha.
Okay, now this time it looks
Okay,
right.
Okay.
Yep.
Makes sense.
Alrighty. Okay, so now we get back to the analysis tab. Everything looks better, right? At least we're not executing, someplace on the stack. And it still looks wrong here. Oh, okay, it just needed time to finish its own updating. All right.
So how did it go on after all?
So we got back to where we are supposed to be, and this is the null terminator. This is part of this. This is T. So this time it works correctly. So I can also upload this code. So both versions are correct now. I just fixed the other one. So the question is, can you document the second one, the quote-unquote organic version of this code, and be able to figure out how it got the same thing done, but with fewer lines of code? It's just a whole lot harder to maintain. All right. So that's something for you guys to do, for quote-unquote studying at this point of this class. We do have a lab today. So let me go back to the lab. This lab is relatively short. It only has the usual quiz type questions, so it should not be taking too long. And I think it's call frame. Yep, I set it up earlier this morning. It already has the right time to release the answer. So I just need to do a save and publish. And it does have an access code of framed. That's the access code. So go ahead and start with this one. I will zip up the program and send it up to the announcement, so that way you guys will get a copy of that. All right, so that's all done. And I'm gonna stop the recording.